Still a few people joining, so I'll just give them a moment. Okay, so I think we'll get started now. There's still a few people joining, but they can join. So I'd like to welcome everybody to this webinar, which is being presented jointly by Core AVI and Presagis. We'd like to welcome you all, and we hope you find this this meeting interesting and useful to you. We're aiming to talk, or aiming to meet for about an hour, but we will be able to stay longer if you have questions that overrun time. Obviously, you're free to drop off whenever you want. We're going to keep questions and address them all at the end of the presentations. So we'd appreciate it if you'd submit any questions that you have using the chat window to enter those questions. You should see on your WebEx screen a logo that looks like that. That will open the chat window for you to put questions in. And when you leave the meeting at the end, there's a short survey, which we'd appreciate it if you'd complete. So without more ado, the companies that are talking to you today. So Core AVI is the world's leading supplier of real-time safety-critical graphics and compute drivers, COTS hardware IP, and embedded graphics processors. Core AVI software has been deployed in over 130 programs in more than 20 countries, bringing 20 or more years of experience with safety criticality to the aerospace and defense industry. Presagis is a technology innovator company and a leading provider of software development tools for HMI simulation and deployment. Since 1985, Presagis has been supplying first-in-class cockpit display system software for both graphics development for ARINC 661 and certifying them under DO 178. Been doing that for about 15 years. We do welcome everybody. So to introduce what we're going to talk about, we're looking to talk to you about how to deliver complex graphics and enhance interaction in the cockpit. Our systems have become more and more complex. This is an important topic right now. So GPUs have been widely used for 20 or 30 years in order to accelerate the graphics display in cockpits, and prior to that on our desktops. We're all used to the vast increase in performance and capability of those tools. And most aircraft that are flying today have some form of graphics, those that have glass screens, of course. Some form of GPU is behind that. And those capabilities have been increasing with what we see, probably starting through the consumer market, as we've all become used to that. But recently, particularly in the military area, but also in the commercial space, there's been a prodigious increase in the amount of data that cockpit designers want to display to crews. Because it's become possible, they've figured out ways of processing data in order to make it more accessible to those crews. But that takes both processing power and increased real estate in the screen. There's also been developing new ways of interacting with cockpit systems. We're going to talk through this presentation taking an example of hand gestures, where people basically wave their hands or form gestures in front of the screen, not actually touching it. Again, started in the consumer world, and it's moving into safety critical and mission critical systems. And there are other new techniques for interaction that are also becoming important. And because of their increased sophistication, those detecting those gestures or following our eyes or watching our head movements, displaying the augmented vision that is becoming common in cockpits today, all of that requires more capability in the compute systems that are behind the glass that form that. So all of that is basically overwhelming the CPUs and GPUs that are available in cockpits today. But there's a new class of GPU that allows for general computing solutions to be deployed. So it's basically general purpose GPUs. It allows general purpose computing using the capabilities of a GPU. So what we're going to talk about in this webinar is basically what is GPU compute, how does it work, what can it be used for, and how you can use it and certify it in safety and mission critical environments in order to deliver these new display techniques and these new interaction techniques. So the agenda that we have today is we're going to talk to you about a bit more about the recent evolution of HMIs and why this is changing. We're going to talk to you about what GPU compute actually is, how it can be used, look at solutions that these companies, the Presagius and Core AVI, can provide to you. And then we'll wrap up those things and take some questions if you have them. The speakers today, we have one speaker from each company. Lucas Freizek is a field application engineer with Core AVI. He's been a software developer and now a field application engineer with Core AVI for 5 years. Got extensive hands-on experience in developing embedded software and in deploying DO-178C safety critical systems. Matt Jackson from Presagius is a technical product manager for the embedded graphics products of Presagius. Prior to his current role, he was a consultant who worked for years on various aircraft developing software and deploying systems in real aircraft, looking at how they worked, and has specialized in this kind of area. Particularly been involved in touch-based systems and in ARINC 661 system, and has been an active member of the ARINC 661 committee for the last dozen years. So at that point, I'm going to hand over to Matt to introduce the first topic to us. Thank you, Matt.
For the introduction there, Paul. So I'm going to take us through, once I've got control of the screen, and just kind of step through some of the HMI, and we're going to look at how the HMI works and what's going on here and what its purpose is, because GPU compute we're going to be talking about, and we're going to use an example to show how we can utilize that with our HMI. But if we go back to the principles of what the HMI there is there for, and it's to present data for a task or role. The reason it exists is actually to do something. It's not there just for entertainment. So the role is there to present the information and allow you to interact with the systems to perform your task. Now, traditionally, most aircraft, the data was there for a single safety critical purpose of flying. So if we look at the kind of display at the top in a kind of older system, it's all about the engines, the speed, the angle of attack. all the things that somebody needs to know to make sure that they can fly safely and there won't be a problem there. However, the kind of task scope has increased over the years. Technology's enabled a lot more possibilities. It's no longer just flight safety, but mission critical. We've added over the past 30, 40 years, more and more roles for the user in a cockpit for an aircraft, but also in vehicles for the tasks that they can achieve or might want to work with. So this task scope has increased because of technology enabling it. So what happens from that is effectively sensors have come along and we can do more. We've got more computing power, we've got more sensors, we can do more and show more. The challenge is obviously with things like external sensors, we've got FLIR, LiDAR, and we can merge scenes as well and do that. So we have all the challenge of these new external sensors, but we don't just have external sensors, we have internal sensors inside for the user. So how do you interact? Head, eye tracking, hand tracking, bio tracking of the user as well. So these are all new things that have to be handled inside an HMI. Now, we don't have to use all of these things, but people want to use these things. And the interesting reason is the external information coming in, it provides a scope increase of the tasks that somebody can perform. So the fact that I can see more outside or read more information from my vehicle or from something, I need to now present that. So there's a huge amount of data that needs to be presented, but I need to interact with it. Hence the need for internal sensors for how do you actually manage, manipulate, and use this data in a way that's relevant and kind of safe. So the HMI challenge is we've got to display data in a format that's usable. Too much unprocessed information makes a task much, much harder to perform. So in the example here, I've got a digital moving map that lots of people are familiar with. The problem is as we add sensors, we can add information, and as we have navigation systems and routing, we can add more information, no fly zones, and oh, hang on, we're getting lots of detection, and now we don't know what we're doing because there's too much information here and it's not necessarily relevant for the task that the person's performing. So we have this challenge of there needs to be some form of processing on the data we present, and it needs to be presented when it's relevant. Now that needs computing kind of processing power to actually make some of these decisions to aid the HMI. Obviously, we've got the presentation of that data. We've now got multiple systems to control. Previously, we would fly or drive a vehicle, and we only had some simple interfaces. We just had to kind of give it some power and point it in a direction and control the systems of the engines and brakes and other things like that. Now we've got roles that are actually involving planning a mission, doing routing, looking at weather conditions, managing subsystems, controlling various components. So we have to look at what type of interactions in the HMI for all these systems require. They need to be intuitive. We don't want the user spending all the time thinking, what button do I press, or how do I grab that thing or change that system or control that system. And the thing is, for user input, intuitive actually can mean different things. So the example I've got here is a music mixing desk. If you look at it, it's got lots and lots of knobs and dials and sliders and various things like that. But actually, it's quite intuitive for somebody who's got training on there, and it reacts quickly for that task. However, if you want to send a text message or do something else, these sort of controls don't make sense. If you're wanting to kind of look at Facebook or other stuff, there isn't information, there's no way of typing, you haven't got that type of control, if you have to slide something to get a text character up like old navigation systems used to do for characters in cars, it's not necessarily the most intuitive way, and you spend a lot of time using the control rather than focusing on the task. Now, the response time has to be appropriate for the systems as well. So when you've got an input device with your HMI, the response from you doing something and something changing in the system, it has to be aligned. For some systems, the timing doesn't matter as much, but for other things, you need to see rapid responses, you need to see that interaction within an amount of time. Now, interestingly, with input devices, consumer devices are starting to heavily influence what is intuitive. So as you go through different types of users and different age ranges and experiences, you find that a device or an input method that was relevant for somebody 15 years ago for the next generation of user is no longer intuitive or is not up to the task. The great example of this is touchscreens. Give a touchscreen to a small child, they can grab it, use it, and a teenager is glued to their phone, and they can actually interact swiping and pinching, and it's intuitive. Put them in front of a keyboard and a computer from the 1980s, and they don't know what to do because you've got to remember keyboard combinations or you've got to remember instructions to type. So these things are having an impact on what's acceptable and what's intuitive, along with how do you manipulate this information. So we've talked about the extra information that is become available and we want to present to a user. And the use of technology has actually enabled us with new sensors and new data. Historically, we were getting limited in a cockpit. You had a certain amount of screen space or cockpit space, and the screens were of a certain size. If you wanted more information, you add another screen or another dial. We went to digital displays, LCD displays, but you'd have to add another LCD display. We've got to the point now where technology allows us to have large areas, so large screens, single surface screens that we can then reconfigure that gives us more space within a cockpit of an aircraft. But also with helmet mounted displays, we can now present a virtual cockpit as well. So we can actually extend the cockpit beyond the physical bounds of the cabin. And if we need information, we can actually utilize the human machine interface by moving a head or tracking a position to actually move more data in and out of scope and actually extend that. So these things are now available, and modern GPUs have the power to shift enough pixels and to render those scenes in these situations. So the modern GPUs got the graphics power to do this. However, the data still needs to be in a format that's suitable for the user. We don't want information that's relevant and cluttering and overloading the workload. So we do need to still think about how we present that data. So we've talked about the presentation. Obviously, I keep referring back to user interaction. Now, traditionally, physical interfaces like keyboards or bezel buttons, moving on later in evolution, we kind of have cursor control, joystick, trackball, mouse, thumb wheel. These type of devices worked. However, kind of moving to a larger amount of information and a larger amount of systems, adding another keyboard for a subsystem doesn't particularly work well. We have to think of other ways of interacting because we can't have a single keyboard for every subsystem. We may have to have one that we share. We may need ways of interacting with multiple systems with a single keyboard. A menu with a mouse or a pointer is great, but again, we've now increased the screen space. So moving my cursor across a screen, historically, if I had a 640 by 480 screen, that doesn't take very much effort to move a cursor and move that around. If I increase that and my screen is now 4000 by kind of 2000, and my actual space is no longer something like 7 inches, 8 inches, and I'm talking about a screen now. We've got 25 inches, 40 inches as a single surface with a wide area display, to a helmet where we've actually got a virtualized screen space where we can actually be moving almost 180 degrees of vision. That's a lot of movement for a cursor. So we need to kind of think of other interaction methods. So things have come along. Touchscreens have become kind of more widely used and more widely accepted because the speed of a person putting their finger where they want to actually interact and not have to drag a mouse cursor has actually helped. The ability to kind of do a gesture manipulation on a screen with a touch is great. But we're now seeing other types of interaction methods that are, do we look at hand gestures? Do we have the head tracking, moving information or controlling what you interact with? Now, these interaction methods lead to kind of some more HMI challenges. So the big thing that happens within an HMI is we've got input and there's a kind of a flow. Somebody does something with a keyboard, mouse, or a tracking system, and the software has to do something with it, make a decision, and then eventually we have a loop that comes back and it gets presented to the user, be it via the display, helmet, a haptic, or audio. But there's a process in there, and there will be a delay from you doing something and actually seeing or getting a response to the user. So in a traditional system, where we had physical devices like keyboards or buttons or even cursors with mice or trackballs, typically if you're using a system like that with a button, so a discrete input, you're looking to try and ensure that the user sees a response within 180 milliseconds. Anything beyond that is typically kind of assumed as the system's not responding. The user starts kind of bashing away at it going, hey, this doesn't work. So this is a kind of common thing that we're always trying to get below 180 milliseconds, but this is a discrete action. So press a button, press a menu on the screen, you expect to see something occur. With newer interaction methods inside an HMI, we have some interesting changes here because actually we've got a continuous input stream. So touch, head movement, hand movement, you need to have some form of feedback loop for the user to know where they're interacting. So it's a bit like a cursor, but actually you're doing a lot more work in between. Now, 13 milliseconds, if we look in kind of statistics that have been taken by people, is kind of the lowest perceptible speed that a human can see for a visual stimulus. So kind of anything below that, people don't notice at all. At 50 milliseconds, kind of that delay in presentation is acceptable. Once we get beyond 75 milliseconds of you moving something and not seeing something in response, users start to anticipate this data, anticipate where things are, and it actually increases the workload on the user. So instead of helping, you're actually increasing their workload because they're thinking and they're guessing where something might be. And typically 300 milliseconds latency is just beyond limits. It's just people give up and it's just unusable in many circumstances. So what does that mean for us? So moving through the next kind of part of this presentation, we're actually going to take an example of trying to do hand gestures. And why is it important? Because actually hand gestures is one of the newer methods that allows natural interaction with a system. Like touch, we can quickly move a hand or we can do a motion or something to control a system or control many items of a subsystem. And it gives an intuitive way, a natural way that people can interact, especially if you're looking at helmet mounted systems. How do you interact with that? You're looking for this kind of feedback and hand movements. You don't have necessarily the same sort of controls. Now, hand gestures exhibit similar issues to kind of online gaming and video gaming. And actually, some of those numbers in the previous slide come from gaming, but also from HMI studies. And they actually correlate, kind of like delays on people doing online gaming. They give up and they find that they're not working. But the same with, it's the same process of actually you do an action, you expect to see a response. And it has the same issue. If I wave my hand and I've got a helmet, I need to see that hand relatively quickly on the screen. Otherwise, I start predicting where my hand is. And if I move my hand around slowly, that's great in the lab, but realistically, when you're moving, driving, flying, that's not the case. Your hands are going to move around, not in kind of very discrete steps and very controlled manners, because other things are going to go on. You need to make sure that your positioning of your hand and the actual feedback loop to you as a user is quick. So we want to make sure that if we're showing a representation of a hand or something else that we're tracking, we want to make sure that kind of latent, anything above 75 milliseconds is avoided. So what we're going to look at is particularly what this means in a system. Now, this is being done. People are doing this type of work. It's not new. It's in the consumer world. And there's different ways of approaching it. You have some form of position sensor, hand position, some form of position recognition or processing, and then you give some point data or location data once it's actually recognized all the information to your HMI. Now, this could be over a network interface or some other thing that's doing it if it's two discrete systems, or if you're using a single processing unit, it could be a sensor that's connected to an HMI platform with some code running in there for the hand position processing. So what we're going to look at is what the consequences of this is and how much power do you actually need to get this working realistically. And at that point, what I'm going to do is hand over to Lucas to look at what this actually means. So this is the example we're going to look at.
Hey, thank you very much, Matt. I'm going to try to take control now. Doesn't look like it's letting me take control. Oh, okay. Just give me. Paul, can you hand me the control? It doesn't appear that I actually have it.
You should have it now. Sorry about that.
Okay, yeah, I just had the prompt. Sorry about that. I should now be able to control it. Thank you very much, Matt, and thank you for handing it over like so smoothly, Paul. So like Matt had just said, I'm gonna go into an example of how hand tracking can work, how we can take advantage of known algorithms to perform hand tracking and why it is more complicated than you might think it is, and how computationally expensive it is. So I'm going to describe a pretty generic algorithm for hand tracking that relies on a pixel array based data that you might get from a CMOS sensor. And the idea behind this algorithm is we're going to pre-process the pixel data, remove as much information that's unnecessary. So we want to filter out parts of the data that don't represent the hand. We want to isolate where the hand is in the scene and then use that information to actually determine the position of fingers and the palm itself. A little bit of background about that to kind of illustrate how a lot of this is going to work is that CMOS sensor will typically give you data in the form of numbers that represent some kind of image coming from the sensor. And so these numbers typically represent the brightness of pixel values, where 0 represents no brightness at all, and the max value, which is typically 255, it represents the maximum brightness. So you have a range from black to white. With color images, it works the same way, but I'm just going to focus on a black and white image right now to simplify things and make it easy to explain for the presentation. So in our pre-processing steps, one of the first things we'll want to do to filter our image is determine where skin is in the image. So most people's hands are covered in skin, and that's a pretty good place to start to determine where the hand is in the sensor data. And so a simple algorithm to determine this is to take the darkest skin color in the image and the lightest skin color in the image and use a filter to find every value that is in between these two ranges. So the darkest skin color and the lightest skin color. And this uses about 2 floating point operations per pixel. And we're going to keep a running tally as we go through to find out how much computation are we doing per pixel to find the result that we want. So to really illustrate why this is 2 floating point operations per pixel, this is all we're doing. For every pixel, we're comparing it against the minimum value, and then we're also comparing against the maximum value. So we're doing 2 comparisons, which results in 2 different floating point operations. The next thing we'll want to do is remove any noise in the image. So our filter before was only looking for stuff that had the color of skin. In an image, there might be more data that fits that filter that does not represent our hand, but it'll be scattered throughout the image and not in a big area like the hand is. So an easy way to do that is just to run a noise filter over our image. And a simple noise filter would be a noise median filter, where the idea behind it is we're looking at a pixel, we take a wider glance looking at the pixels around that one and average the value and then store that result. So the example here, we're going to take a 3 by 3 pixel area, average it, and then use that as our final result. And this results in about 9 floating point operations per pixel. The reason it's 9 floating point operations per pixel is the fact that we're doing 8 additions in 1 division. So here we can see an example of how that math is actually working out. So we have a 3 by 3 area of pixels. We're going to add up all the individual pixels in that area and then divide the result by 9, which is the number of pixels in that block. So 8 additions, 1 division is 9 different floating point operations. One of the last big steps for the pre-processing is going to be determining the outline of the hand. And a very common approach to handle finding outlines in image data is to do something called a standard deviation filter. The idea behind here is that we're going to take this equation that's represented on the screen right now and apply it against every pixel, which results in about 17 floating point operations per each pixel. And you might be thinking, what does this equation mean? It doesn't look pretty straightforward, especially if you haven't, touched math since college. And it's really just the general form of a standard deviation filter. And if we were to implement it as it's described in math, it would be very computationally expensive, but we're going to take a more optimized route in order to implement it. And we're going to do that by using something called a convolution. And if you've paid attention to computer vision or neural networks and machine learning and that type of stuff, you've probably heard the term convolution thrown around a lot. And so I'm going to explain what exactly is a convolution and show that it's not really that complicated. It's just a series of additions and multiplications. So to perform a convolution, we need some pixel data that we want to apply and a filter to apply against that pixel data. So in this case, we have a filter on the right here, and the numbers in it are specially chosen to implement the standard deviation filter. We're not going to be worried about how those numbers were chosen right now. You just need to know that this is, it's been proven in the past that this implements the standard deviation filter if you apply it using a convolution. We have our pixel data, and since we have a 3 by 3 filter, we're going to apply it against a 3 by 3 pixel area. And the result it gives us will represent the pixel at the top left of this area. So what a convolution is going to do is piecewise, we're going to multiply the pixel value by the filter value and add it to a running sum. So we'll take the 255 at the top left, multiply it by the 1 in the top left of the filter and get the value 255, and then add that to our running sum. We'll repeat this for every pixel in the 3x3 area and for every filter value in the 3x3 filter. So the next one would be 127 times 0, which results in 0, which we add to the running sum. Then we do 255 times 1, which is equal to 255, and then we add that to the running sum. And we repeat this for every value until we have a completed running sum. We'll just keep going. So this results in a final sum of 637. Since all of our pixel values are in the range of 0 to 255, we take the result and then we clamp it in that range of 0 to 255. So 637 now becomes 255. So we're repeating this exact same process for every pixel, where we're doing 9 multiplications and 8 additions, which is 17 floating point operations for every pixel in the image. At this point, we know where the hand is in the scene. We have an outline that shows where the hand is in the scene, and we can use that outline in a specialized algorithm to determine where the fingers are. So that is going to look at the outline, find out where the thumb should be, where the index finger should be, and where the other fingers should be. I'm not going to go into detail about how this final part will be processed. It's less computationally expensive than everything else we have just done at this point, since we have less data to work on, and it won't add too much to the final analysis of how expensive is this computation. Once we have all the finger positions, though, like Matt said before, we can take this information and pass it to the HMI application, where it can use it to do gesture recognition based on how the fingers have been moving in time. So let's assess, all the work we just did right now. For a modern system where you're doing hand tracking or some kind of tracking, you'll want to use a high resolution and high frame rate input feed. So I'm going to operate on the assumption that we're using a 1920 by 1080 input feed that's running at 60 hertz. So that means we're getting 60 frames in 1 second of data. And the reason I'm using this assumption is because for user interfaces, we want high resolution to give us lots of precision in how the hand moves. So if there's a small movement in the hand, we'll be able to pick that up. And then we want a high frame rate to actually have a responsive display, as we'll only be able to sample the motion on every new frame of data. And so if we aren't sampling at a high enough rate, there'll be latency in between when the hand moves and when the system is actually able to pick it up. So if you kept track of the run of the number of operations we've been doing per pixel, you're looking at around 28 floating point operations per pixel. 1920 by 1080 display, 28 operations per pixel, 60 times per second. We're looking at 3.4 gigaflops, or billion floating point operations per second. So how does that compare to what a CPU is capable of? 3.4, it sounds like a big number, but we have really nothing to compare it against right now. If you look at a modern Intel i9 system with operating under the assumption that it's only using a single core right now, it has around 6 gigaflops per core. It's capable of doing 6 billion floating point operations per second. And this is when optimized using its single instruction, multiple data extension. This is using vector operations. And so if you take our 3.4 gigaflops and compare it against this, just pre-processing the image uses 50% of the available computation on the CPU. And this, okay, sounds great. We still have 50% left, but you do have to keep in mind that the CPU has other tasks it needs to do than just run our specialized algorithm. It still needs to run the operating system. It still needs to run the other applications on the system. And if you wanted to do the hand tracking on 2 different cameras instead of just one, you've gone over your entire computational budget that the CPU is capable of. Now, if we compare this to a GPU, and I'm going to use the example of the AMD E9171 here. This GPU has roughly 1,200 gigaflops, so it can do, basically 1.2 trillion floating point operations per second. pre-processing of this data is using 0.1% of the computational power of the GPU. So there's lots of leftover compute time on the GPU to run our graphics, run other compute applications, or anything else we need. So before I go into more details about GPU compute, could we reframe this problem in any way to make it more viable on the CPU? And yes, we can, but there would be trade-offs to do that. So two obvious ones based on what I had said before are reducing the image size, which has the trade-off of giving us less accuracy, so we won't be able to pick up small motions in the hand anymore, or reducing the input frame rate, which would add latency. And based on what Matt has told us before, increasing latency is not very viable in high stress situations like the cockpit, where you need to make sure that the user doesn't really need to think about what they're doing. They're just able to do it and the system responds quickly and accurately. Some other things that could be done is to increase the core count of the CPU or to use multiple CPUs. So I had said that we're looking at a 1-core CPU. If you increase that to 8 cores and assume linear scaling, you get roughly 48 billion floating point operations per second that you'd be capable of doing on the CPU. But this also does add some complexity. Running on multiple CPU cores, you now have to worry about multi-threading in your implementation since you're going to be sharing data across the CPU cores. We still have to worry about interrupting the work. So if the CPU needs to do another task, we could stutter the input since it's switching what task it's working on. And then using larger CPUs or more CPUs increases the size of the CPU itself, the IC, and the PCB that we need to mount it off. So this increases the size and weight, and also increases the power usage when you're using multiple CPUs or multiple CPU cores, which in cockpits today, size, weight, and power is a critical thing that everyone's been focusing on. So this kind of goes against what the industry trends are right now. So why does this gesture recognition hand tracking fit so well with GPU compute? And the reason is because GPU compute is very good at a specific type of problem. And these are problems that parallelize easily. And so in computer science, there's a term for these types of problems. They're called embarrassingly parallel problems. And these are problems where we can operate on data independently and in parallel without having to worry about synchronization between two different processors. And so the hand tracking algorithm we just described before, where we're looking at pixel data, each pixel is processed individually, where it only has to look at the immediate neighbors around it, but it doesn't actually change the image at all when it reads that data. We're only reading it off. So each one can be processed individually. And so if you process 10 pixels at once, they can all be done in parallel without interfering with each other. And since this is a problem that parallelizes easily, we get the full compute performance of the GPU, giving us that 1.2 trillion floating point operations per second that the 9171 is capable of. So to go a little bit more into what GPU compute is, it's really just a way of doing high volume computation on GPU in parallel. And when I say in parallel, I mean working on the data in parallel and also doing it in parallel to what the CPU is doing. And we're talking about thousands of multiplications and additions per frame to millions of multiplications and additions per frame. And it's really not specific to any one class of problem. The real idea here is that we're using the GPU as a general purpose math accelerator for whatever kind of computation we need to do. So modern GPUs follow kind of a similar architecture where they have hundreds to thousands of vector processing organized into different cores. And on the right, I have an example of this. So you'll have one core that'll have some number of vector processing units in it. And typically these units are used in graphics to process vertices or pixels in parallel. But we can also repurpose them to do any kind of general purpose computation on a modern GPU. And really the idea here is that each core is going to be running an identical program, and the vector processing units in that core are going to operate on a common array with different offsets into that array. So you'll have one core running an identical program where the first vector processing unit is going to operate on the first set of data, the second one on the second set, and onwards. And this array of data in a graphics context would be vertex or pixel data, but in a general purpose GPU compute application, it would be anything that we can represent as an array of data. So this could be a digital signal. It could also be image data that we want to process in a non-graphics way. But again, it can be anything. The GPU doesn't care what it's processing as long as it's represented in a way that's accessible to the GPU. So some use cases of GPU compute to kind of illustrate how it's currently used in the market today, or just in general today, not necessarily in this market, but future use cases of it. So a very common use case of GPU compute is for object detection using state-of-the-art neural networks, specifically convolutional neural networks. And the way that these are implemented is no different than the algorithm I described before, except that the volume of computation just increases significantly. So you're still processing things on a per pixel basis, but instead of running simple filters on them, you're now backing each pixels with layers and layers of a neural network where they're doing multiplications and additions to implement some kind of machine learning algorithm. And it just ends up being thousands to millions of filtering operations that result in millions of computations per frame. Another big use case for GPU compute is degraded visual environments, where we're doing image processing operations to assist the pilot in low visibility conditions. So we're going to take some feed from an external camera to enhance it using the GPU and external sensors to give the pilot a better idea of where they're flying in low visibility conditions. So this could be used, to assist the pilot in finding the landing pad in a dust storm, or finding some location in the dark. These types of applications where you can't rely on vision alone to know where you need to go. And the last common use case of GPU compute is signal processing. And so this is when we're taking some data that is coming in over time, and we want to do a Fourier analysis on it. And so Fourier analysis lets you look at data in the frequency domain, so you can see, how frequently or how much of a certain frequency exists in the data set. And so we can use the GPU to accelerate this type of computation without relying on an external DSP. Right now, there exist a few GPU compute APIs. Two that I would say the audience is probably more familiar with are OpenCL and CUDA. OpenCL is a high-level compute API defined by Khronos. It's able to run on a number of devices, and it's vendor agnostic. It's an open standard that anyone can implement. But a real downfall of OpenCL, or two real downfalls of OpenCL, is that one, it doesn't have support for graphics. There's not an easy way to connect it to OpenGL or any other kind of graphics API to draw. It requires multiple copies, and it's not very friendly to the user. The other big downfall, especially in the aerospace and defense market, is that there really isn't a path to certification for OpenCL. So there is no proposed standard right now for a safety critical variant of OpenCL. And so, safety critical systems, it's not really an option. The other big standard is CUDA, which is a high-level compute API defined by NVIDIA, and it's vendor specific. It's only implemented on NVIDIA hardware, and like OpenCL, it doesn't have a path to certification. So in a safety critical system, it's not really an option. There's a new standard from Khronos, the same people who define OpenCL, called Vulkan, that provides a high-level API for both graphics, and so you can do compute on the GPU, and then you can share the data with the graphics core, or vice versa. You can do graphics on the GPU and then post-process the results using general purpose GPU compute. And it's like OpenCL, it's vendor agnostic. It's an open standard. It can run on CPUs, GPUs, FPGAs, whatever devices want to implement the standard. And there's actually a path to certification for it. So there is a standard being defined for Vulkan safety critical, just like the OpenGL safety critical standards. And Core AVI actually chairs the safety critical working group for Vulkan, and the current Vulkan safety critical standard is actually based on our original proposal. Another big point about Vulkan is that to be conformant to Vulkan, you actually have to implement support for GPU compute or compute pipelines. So GPU compute is always an option when you have access to a Vulkan driver. The last thing I'm going to talk about right now for GPU compute before I hand it back to Matt is the safety critical concerns about GPU compute. And like when you develop software running on a CPU, there are concerns about developing software on a GPU. And so you have to be worried about things like the worst case execution time of your code that runs on the GPU to make sure it doesn't interfere with other software running on the GPU. And also you have to be able to do code coverage analysis to make sure that the code that you write to run on the GPU actually implements what the source code says. On the CPU, it's a very evolved ecosystem. There's tools that exist for multiple vendors to assist developers in doing this kind of analysis on their programs. On the GPU, these same tools don't exist today. The ecosystem isn't as evolved. Safety critical GPU compute is relatively new in the safety critical market. And so a lot of this analysis currently needs to be done by hand. One thing I'll take note here, and I'll go into it towards the end of the presentation, is that Core AVI does provide a number of GPU compute libraries that actually implement the shaders ourselves. So we worry about worst case execution time and code coverage analysis and that type of thing, so that our customers don't have to. That being said, I will hand it back now to Matt to wrap up the HMI compute usage.
So Matt, I'm going to give you control of the screen. I'm afraid we're running over time a little bit, so you'll have to speak quickly, Matt.
Okay, I'll see what I can do.
There you are.
Okay, so thank you for that kind of background on the compute. We used this example just for hand tracking, just as an example, because it's actually an input, but you can see the actual data processing is relevant for all type of HMI. It is this we were talking about HMI input, but obviously this could be for output as well. So just to kind of refer back, we've got an input, we've got software, we've got an output here. How that works without compute today in an environment, typically it comes in, that data comes in, there's some processing that you've got to do on data, be it for hand tracking, or if it's actually processing for the data to show on the screen and how much to show on the screen. There's an HMI modeling model that you're trying to present in a particular way, and you've got some rendering that then talks to a GPU. Obviously, the challenge with that, you can see in this particular case with a hand gesture, the latency, there's an issue possibly here. If I'm trying to use my platform and I want to make use of this single HMI platform, the computing power locally, it could be taking up to 50% of the CPU budget just on a high-end CPU, just for the tracking of that hand on the screen. And obviously the computations, it could mean that that is kind of between 32 and 48 milliseconds, not even considering the kind of gesture recognition that we may want to do. So kind of grabbing and pinching and doing the recognition of a pattern or things like that. We haven't even considered that. We're just looking at the hand tracking as a data stream of X, Y effectively in this particular case. But you can see that we're hitting a processing time where there is an appreciable amount of latency starting to appear using all the computing power on there. With a compute solution, you've still got data coming in. It still has to get in. But the interesting thing is the HMI data processing. So if it's for an input, or if it's actually for a data set that we're trying to present on the screen, we can offload a lot of this processing to the GPU. Now, one of the interesting things, and I think Lucas touched on it very quickly there, is with Vulkan, we can actually share data within the GPU. So we don't actually have to get the data back out of the GPU necessarily. For the hand gesture, we'd want to do that for some of the ways that we recognize patterns and interact with objects. But for some situations, we can actually use the data processing on the GPU, and because the HMI drawing, the actual physical, where do I want things on the screen, has to go through the GPU, we can access that directly, data directly on GPU. We don't have to come back out to CPU, operating system. We can actually have an array of data points ready for the HMI rendering pipeline to access in the GPU. That improves the whole throughput. So we can do some very complex things and accelerate that all through doing data processing and manipulation in the GPU, but also using that same GPU to be rendering that scene. So for an HMI, this really helps. So in this particular case, it's possible to be down at 16 milliseconds. It could be that we could do a whole frame, have the data ready, and do something. So we've got a much lower response time before we see something on the screen compared to just using the horsepower of the CPU, which means drawing complex things, the latency's improved. Now, 48 milliseconds it's still acceptable, but you haven't got much headroom left. You haven't considered all the other tasks your CPU is doing. You probably want it performing other tasks at the same time. So you want to relieve it of some of those tasks. And if we can offload a whole load of this computation into the GPU, it gives it more time to do other tasks in the system. So how does that work? So we've talked about this particular example, which was a hand gesture, but HMI procedures have an HMI development framework. So we can actually develop an HMI model, generate code from it, and that HMI code goes through a runtime, and then we use what is known as a platform abstraction layer to hide ourselves away from the very low level details of the CPU and GPU. But we've historically always had the ability in our models to interface bespoke or specialist components. So we've done for years things like digital map interfaces so that the actual model stays the same, but you can actually have a platform specific in the abstraction layer of the map object rendering tree or anything specialist or external. We have the same, and we've done this for things like ARINC 661 and in the face environment where you have an external video source. Now that's generic, but actually the implementation is very hardware specific because that actual video may be in face, and I've forgotten the terminology in OpenGL, but effectively it's a buffer that you're using, a compositor, but it might be a video stream coming over a network card. It may be something else. So we've allowed people to design this, and we've had in mind that we need to be able to have access and encapsulate this in such a way that we can take advantage of new technology, new APIs, new systems and subsystems. So it means, obviously, for the hand gesture, we could actually have a convolution object. So we're looking at, hey, here's the tracking, and you've got all these things that the systems have fed data. We may be tracking a hand, we may be tracking something in space as we're flying around from a sensor, and we're wanting that to actually narrow it down and give us bounding boxes or something like that. And we could have a convolution object here, and that code we could have executing on the CPU. Now, obviously, we would go, well, that takes a lot of power and things like that. But if we want, we can actually keep our model the same and say, well, actually, we'll have a specialist Vulkan piece of code that's running our algorithm in there. And instead of running it on the CPU, we can run that execution code on the GPU and take advantage of that. So it's one of the things we've thought about in the Procedures HMI development frameworks of how can we take advantage of new APIs, new technology, and where we can offload tasks as well. So Lucas is going to talk a little bit about what Core AVI offers in terms of a compute platform. You've seen how I've just gone very quickly how some of our HMI framework can take advantage of that, but there's a reason why we can do that. We've thought about how do we encapsulate and support new standards and new approaches. We've been doing HMI development tools for over 35 years. In fact, we started off with avionics HMI engineers who built the tool at the beginning, and we've had to support huge amounts of technology change. So we've worked with vector, stroke-based displays, pixel-based displays, and then as APIs like OpenGL became available, or OpenGL SC2 with shaders, and now Vulkan, we've hooked onto that. We've also hooked onto things like recently we added components for gesture recognition for touchscreens, which are operating system agnostic. Now, in the commercial world, these things are all built into your operating system, Android or Windows or Apple iOS. We actually had to do that work and work out how we get that input and process it as part of an HMI. So we're used to adopting new technologies and things. And one of the reasons why we're familiar with that is kind of working with standards. We've had a long time working in the ARINC 661 world. So we were actually involved in the ARINC 661 world, and some of my colleagues started working on that standard back in 2003. So we've seen the evolution, we've supported it, we've understood, we've submitted new ideas or spotted issues, or as we've implemented things, we've fed it back because we think it's important that industry we kind of contribute back to that. We've also been part of FACE, which obviously in North America is very, very important. And inside there, we've actually been part of the graphics subcommittee since 2011. So again, part of it being involved, understanding the day-to-day problems of building HMIs, integrating the systems and things. And as Lucas mentioned, Kronos with the safety critical, we've actually submitted and been part of safety critical profiles in Kronos for graphic standards. So this really helps us with our understanding of how we can take advantage. Now, this example we talked about was with gestures, but you should be able to see that it's not just gestures, it's the processing of the data for the screen, as well as the input we can take advantage of GPU. Now, all of this work we've done is safety and mission critical. We've spent a lot of time working in systems like that, and we've actually had over 20 years. Our first certifiable environments we were doing back in 2000. So we've been doing certification of these HMIs for a long time. And our software and tools have been used worldwide to actually do this. So we're flying and driving in vehicles and planes and helicopters worldwide. So it's not just one regulation people that have checked over how we do it. We've had multiple regions do that. So this is how we support that in there, and how we can take advantage of the newer methodologies. So what I'm going to do is just hand over to Lucas, who's going to just explain what Core AVI do to help support compute in these environments as well.
Okay, thank you very much, Matt. I will try to go over the last section as quickly as possible so we can get to the questions that you guys in the audience have.
So some people are leaving at this stage. So if you can wrap up as soon as you can, Lucas, you should have control now.
Yeah, I'll go through this quickly. So like I alluded to before, Core AVI has kind of a stacked approach to how we're supporting compute. We have our underlying Vulkan driver, which we call VK Core SC, and then we have compute libraries built on top of that to make it more user-friendly and easier to use in safety-critical environments. We also have libraries for non-compute related things like OpenGL, video encode and decode for H.264 and H.265 video, and GPU safety monitoring, but I'm really going to focus on the compute core and VK core VX here for basic linear algebra subprograms, fast Fourier transform, and AI and video processing. So our solution, like I said, is a stacked solution where we're providing a underlying Vulkan driver that has high performance, low level access to the GPU. And if you have a very specialized application, you can use Vulkan directly to get the performance, but then you also have to address the safety critical concerns yourself with writing your own code that runs on the GPU. We have our user-friendly libraries like Compute Core and VK Core VX, where we're providing open standard approach to implement higher level functionality where we're dealing with the hard parts of GPU compute. We're implementing the shaders, we're making sure the shaders are certifiable, and we're providing all that evidence to you guys. So our compute core product provides basically math acceleration, namely basic linear algebra subprograms for highly optimized vector and matrix math operations, and then also fast Fourier transform for doing signal analysis and Fourier analysis. And like I said, certification evidence is available for everything here, including code that's running on the CPU and GPU. We have our VK Core VX product, which is a relatively new announcement where we're supporting the OpenVX standard from Kronos. So this is a high-level compute standard from Kronos that's meant for computer vision and neural network inferencing. So it provides a method to doing, the computer vision type stuff I described earlier in the presentation, as well as neural networking, where you can build a neural network in the tool directly itself, or you can using common frameworks such as TensorFlow or PyTorch or anything like that, export to a common format called NNEF, and then import that into our platform. So you can keep doing the same work you're doing in a lab right now using common industry tools such as PyTorch and TensorFlow, and then migrate to a safety critical platform afterwards with little issue. And like I said before, we're providing both evidence on the CPU and GPU code here, so customers aren't writing their own shaders and they don't have to worry about certifying code that's running on the GPU. Lastly, their Vulkan driver, which is compatible with many modern GPUs such as the AMD 9171, the i.MX8 Quad Max from NXP, the next generation ARM Mali G78, and more. It's extremely portable across different operating system and hardware combinations. So your software is available to run on ARM, PowerPC, x86, whatever, with whichever real-time operating system you need, and we provide the certification evidence for all of that. So that's the end of my spiel there, and so I'll hand it back to Paul for the wrap-up.
Thank you, Lucas. Thanks for doing that. I think I'm going to skip over most of the wrap-up. I'm sure you've all been paying attention through this. My apologies that we've run over time. We weren't intending to do that. If you would like to get a copy of this presentation so that you can study it in more detail, then please just drop an email to egmarketing@presages.com, and we will send out a copy of the presentation to you. We do have some questions that have been submitted through the chat window. If anyone has anything else, then please send those in now. As I mentioned before, when you exit the presentation, please do complete the survey when you leave. So now, we've got a few questions here. I have mentioned, somebody asked whether the presentation is available. It is. You have the email address on screen. Please drop us an email at that address. Matt, this question is for you. The latency values that you mentioned in this presentation, they're based on some kind of human forces standards. Can you comment quickly about that?
Yeah, these are, so some of the numbers there, so the 180 milliseconds is kind of from general human factors. If you look in the ARINC 661 standard, it talks about anything beyond 180 millisecond latency. For some of the more newer side, these are based on research, so they're not standards. They're studies that have been performed and kind of available, and I've collected some of these numbers together. They're actually some from gaming, where people have analyzed that. Some of it is literally from studies where they're looking at human interaction with this, but these are not standards. It's kind of more research and advice of what they've seen and recorded. So it's not saying this is a must, you must conform to 75 milliseconds or things like that. A lot of this is still system decision and based on your needs there.
Thank you. Lucas, this one's for you. How does computational power translate to power dissipation in the GPU? And can the GPU be throttled in order to reduce power consumption?
Thank you for the question, Paul. So the more work you have the GPU do, obviously it's going to generate it's going to consume more power and generate more heat. So those cores I described before, they're essentially always operating. So if you're not taking advantage of them, you're wasting power. But for cases where you don't need the full power of the GPU, all the modern GPUs we support have the ability to clock down and use fixed clock settings, so you can reduce the power usage of them by underclocking them and having them run at lower speeds or disabling certain parts of the hardware.
Okay, thank you. Another one for you, Lucas. Is there an anticipated timeline for Kronos to adopt a safety critical version of Vulkan?
So there isn't a timeline right now. I believe one of the big current questions about the Vulkan safety critical standard is having multiple implementations. So currently Core AVI is the only company that has a fitting Vulkan safety critical driver. And Kronos is waiting for either a competitor to implement a similar API or to have a reference implementation made.
Okay. This is a question for both of you. Is a single camera is it good enough or reliable enough to be used safely in a cockpit? Is a single camera reliable enough for detection in order to be used in the cockpit?
I think it's a question that can go towards both Matt and myself.
That's
From
right.
Core AVI's perspective, I don't think a single camera would be sufficient. You would want multiple cameras or sensors to give a more reliability to the data that you're obtaining. Relying on a single sensor would be dangerous. If there's some kind of error with that sensor or some kind of fault, then you've entirely lost that system.
So I'm going to concur with Lucas on that one. Is typically we're looking for some form of redundancy. If this is the only means of control of your HMI, it would cause a problem and degraded performance of your HMI, which could cause a safety problem. However, if this is not the primary one interface, it's just a kind of a useful thing that aids productivity and doesn't affect the safety case, there may be a reason why you don't, but typically you would look for more than one. You also would want possibly more than one as well if you're looking, in our example, we're talking about a position in 2D space. If we were looking at 3D and actually motions forwards and backwards, we'd probably want some form of stereoscopic anyway on there. But typically, the actual number of sensors is dependent on your cockpit and what its usage is for. There's got to be a safety case performed for it.
Thank you. Question for you, Matt. Does Procedures interface to Vulkan today?
So we've worked with the Vulkan, some of the Vulkan drivers. We don't have a native graphics API that we're calling at the moment, but we've worked with the Core AVI environment where they're providing some of the support libraries, and we've actually run on their Vulkan drivers. They have, as you probably saw in Lucas's presentation, some extra support libraries, and we've been using those directly. In the future, we'll be looking at using more direct access as we want to take more advantage of some of the capabilities Vulkan has.
Lucas, is there a location where all the supported graphics drivers that are listed for VK Core SC?
So if you go to our website, you should be able to find that information. We list, all the GPUs we currently support, but if you have some more specialized needs, I would encourage you to reach out. We're always open for discussion and finding out what, we're not currently supporting in the market and there might be a need for.
Another question for both of you. If this hand detection algorithm is so computationally expensive, how do commercial low-power cell phones pull it off?
I'll take the first stab at that one. Earlier in my presentation, I talked about ways that you could reduce the computational expensiveness of the algorithm, and ways to do that was to reduce, the resolution of the image and the frame rate of it. On a commercial camera, you're typically getting input at 20 to 30 frames per second, so it's a lot more latency. It's not being used for a high reliability system, and more complicated setups right now already take advantage of GPU compute on commercial drivers, which has been exposed for a number of years. So this is kind of applying that same technology we see in the commercial space and allowing it to be used in safety critical environments with that, a safety critical implementation that meets all the requirements for safety critical software.
Matt, do you want to say anything about that?
No, I think Lucas has covered it. I think there is a big difference on commercial handsets for cell phones and things like that. They are taking advantage of the GPU compute. So they are already doing this. They have very, very good compute processing in there and very optimized. And the way they're doing the sensor is actually a lot lower level of kind of data, but it works for that type of environment.
Okay, so the last question that I have at the moment, this is for Lucas. If you have a GPU that's doing compute and it's rendering graphics, do the two compete with one another, or how do they work together at the same time?
So this is a question that really depends on which GPU you're talking about. So some of the more modern GPUs have concurrent compute or concurrent pipelines, and so some of those pipelines might support graphics, some of them might support compute, some of them might support both, and these would be like the command buffers that the GPU internally has. And so if you're running on a GPU that has that kind of support, they would be running in parallel, processing commands in parallel, and then dividing it up against the internal hardware in the GPU. If your GPU doesn't expose this kind of, or does not have this kind of functionality, it would be the same as running multiple applications where you submit a command stream, the GPU will operate on that command stream and then move to the next one. So you'd have to, batch when you're sending instructions to the GPU, which APIs like Vulkan give you much finer control of when commands actually get sent to the GPU and allow you to really coordinate access between multiple applications.
All right, thank you very much. At that stage, I'd like to thank both speakers for interesting presentations. I'd like to thank everybody who's attended, and especially those who stayed into our overtime period. I'm sorry we've gone 20 minutes past the hour. If you want to get a copy of the presentation, please email the email address on the screen. If you want to talk to anybody, you can also contact us at that email address, and we'll pass it on either to Prestigious or Core AVI, whoever is relevant to that. Otherwise, thank you very much. Thanks for attending.